Okay, here we go. Let's see. Where's my pen? All right, so let's zip through these. Evaluate the expression. So how are we going to do this? Look at number one. There's two things being done to the number 216. That's the base, right? What's being done? What are the two things being done?
It's being cube root.
I'm cube rooting it, and I'm
all to the fifth power.
to the fifth power. Okay. So let's do in that order. Let's take care of stuff, right? So what is the cube root of 216? Now cube roots. I'm going to give you I haven't done this, but I'll give you a list. I'll put it on Moodle. It's 6. It is. 6 times 6 is 36, times 6 is 216. So it's 6. So then this becomes, after we take care of the cube root, jeez, yeah. There we go, how's that? There, a little better. Okay, so this, if we take care of that first, we're going to get 6 to the 5th. And what's 6 to the 5th? Now, this is not really an algebra thing, but I want you to just kind of start more and more thinking about how you can be tricky with getting these numbers, big numbers, right? And well, because it's related to algebra. The parts of your brain, if you look at a real-time PET scan of your brain.
You mean CAT scan?
No, PET scan. So it's
Then why isn't it algebra and whatever this?
well, I mean, because the standards that we're addressing are algebra standards. But if you want to get better at algebra, doing mental math that makes you better at algebra. Just like bench pressing makes you a better football player.
Holy crap,
Right?
okay. So
It's not something that's directly, you're not playing football, but it adds to your capacity to be a good football player, right?
So what does the PET scan show?
It shows that the parts of your brain that are active when you're doing algebra are the same parts that are active when you're doing mental math.
Okay, so question here. So the 3 cube root 216
Mhm.
automatically just changes to 6 and then it's gone.
It's gone.
Okay.
Yeah, we changed it.
gone.
I mean, it's the same thing, but it's just a different form, right? So now 6 to the 5th. How could we do that? Well, there's a couple ways you can think about that.
Let's do 6 times 6 and then 36 to the third.
Okay,
Easy peasy.
well,
7,776.
done. How'd you get that so fast? Pretty good.
We got, you already know what I did too.
Now just go wait a little bit. Okay, so we could be tricky about this. We know that 6 to the 5th is 6 times 6, etc., 5 times,
So
right?
216 times
Okay, good.
216, which is
Okay.
so what? 2, 6, 10
But what is, we could also write this as 6 cubed times 6 squared, right? Because when we multiply like bases, we add exponents. Or we could think of it as 6 cubed times 6 times 6. What's 6 cubed?
216.
Yeah, it's 216. We knew that because the cube root of 216 is 6, right? So that gives us automatically, that tells us that we've just got 216 times 6 times 6. Well, 216 times 6 we ought to be able to do pretty easily. Now, how are we gonna do the math for this? How could we break this down in our heads to
Are
do
you
it?
not going to let us use a calculator on this test?
No, I will, but I just want you to, what's that? Yeah.
So those be like, I can't do this in my head.
No, you don't have to do it in your head. But my point is just that if you do this stuff in your head sometimes, it's okay, hey, listen, I need everybody on track here. I got too many side conversations going on. This is my warning. I'm getting a little tired of it. Okay, so this is like, I coach track, right? So when I'm teaching people to be fast, right? I'm coaching them to learn how to sprint. There's a lot of things that go into that aren't just out there running a workout, right? It's the same thing with any kind of athletic performance. You have to build up. Most of sprinting is at the neurological level. It's developing a high degree of neuromuscular coordination. That's mostly what it is. That's how you get fast. You get fast by training your body to execute all the right forces next to the right motions at exactly the right moments. That's how people sprint fast.
So even if you're not skinny, you can still sprint pretty fast.
Yeah, you can improve your top end speed. You improve by training yourself, like by doing lots of drills to train your body how to move your arms and legs in the right. Because people don't naturally sprint very well; they have to be taught to sprint well. But it takes a long time. You have to develop this neural capacity. You literally grow. The axonic circumference increases all through your trunk, through your spinal cord, into your, so you literally get stronger nerves, but most of it occurs in your brain. Most of it is in your brain where you get these little finger-like projections that fan out through your brain and they interconnect the neurons in your brain. And so that's how you get better at doing things. That's how you get smarter, either in an academic way or an athletic way. And honestly, athletic performance is a kind of intelligence. When they cut Albert Einstein's brain into thin sections, what did they find? Was it abnormally large? No, it wasn't. It wasn't at all. It was a normal-sized brain. But he was an unbelieving, genius among geniuses, right? What was so unique about his brain was that it was very, very dense. It had lots of dendrites and axons, those little spider-like projections that thread throughout your brain and connect the neurons. He had a hugely abundant supply of those things. How did he get them? Part of it was just genetic, but the bigger part of it was that his whole life he did lots of thinking. And when you think hard about big stuff like this, even when you think hard about things like this, it forces your brain to respond, and your brain responds in a couple different stages. The first stage is, and this is part of why sleep is important too, when you practice something, when you learn something, the first thing the way you learn it is you relate it to things you already knew, which is why it's hard for babies to learn stuff initially because they don't know very much, right? But as you start to develop some knowledge about the world around you, you just say, this is kind of like that, so I can use some of those connections, right? And eventually you start to just create new connections that branch off of those, right? They start off, they're really tiny. They're just a couple cells thick. But then when you go to bed at night and you dream about stuff, have you ever noticed that, like, if you're studying for a test, this might be almost kind of annoying. If you're studying for a test really hard, like a final or something, do you ever notice that you kind of dream about that stuff? I mean, maybe not directly, but you will. In college, trust me, you will. I mean, you kind of start to just rehearse that stuff in your head a little bit. Like when I'm doing lots of programming for my other, my curriculum job, if I'm really cranking on that stuff at night, I hate it. At night, I'll kind of start thinking about coding. When I'm going to bed, that's not necessarily a good thing, but it's doing it for a reason. My brain is rehearsing those connections so that I'll learn that's something I'll retain. It becomes part of my interconnectedness in my brain. It's knowledge that I've accumulated. And the good thing about it is you can use it for other stuff. So if you want to get smarter, I think I might have told you this before, one way you can literally get smarter is if you're right-handed to eat with your left hand at dinner at night. It's
What
because
if you do it both?
say it again.
What if you do it both?
If you're ambidextrous,
I'm ambidextrous.
then that's not going to help you as much. But if you're not ambidextrous,
So you call me dumb?
I'm not. If you're not ambidextrous, it's really difficult to coordinate that motion, right? Because you're not used to doing that. You haven't trained yourself. But stuff like that,
Prove it. I'm just kidding.
stuff like that is really demanding of your brain. Your brain doesn't have the network of connected neurons to help your body understand how to make those motions. And when you challenge your brain in ways like that, where you're trying to do something it's not used to doing, that's really demanding, it forces your brain to make those connections. And what's cool about it is those connections can then be used for other stuff, like math or skiing or whatever. I mean, it's something that they're there, and as you become more intelligent, you just become a more capable person. You're able to use this, this capacity in your brain for other stuff. And you'll notice people that have a lot of capacity are just good at everything, right? Because they've worked hard at things and they've developed the capacity, to think in different ways, right? Both intellectual thoughts and like athletic thoughts, right? Okay, so anyway, but I digress. So this kind of thing is important to do, in other words, right? This is like lifting weights for your brain. So how could we do this? How could we do something like 216 times 6? How could we break that down strategically in our brain and just think through this? I could break 216 up into what two parts maybe? 216, right? So what's 6 times 200? 1200. Okay, now hold that in your short-term memory, right? So that's your brain's working. So you got your 1200. Now what's 6 times 16?
44.
Well, 6 times 10 is 6. It's 96. So I've got 1200 plus 96 is 1296, right? See what I'm getting at? So
then
there's
1296 times 6.
times 6. Then you end up with 12, so you can put that
12
behind
times
you.
6 is
1296 times 6. Okay, so what would 1200 times 6 be?
So 1200?
Mm-hmm.
Isn't it 3600?
No, 1200
Oh,
times
1200.
6. 7200. Good.
Alright, because 12 times 6 is 72. Add the zeros.
Okay, now 6 times 96. Now that's hard to do. 6 times 9 and 6 times 6, those are big numbers to try to keep track of, but we could be smart about this. We could
6
say
times 9 is 54.
6 times 100 would be what?
600.
600. So I've just got to subtract away from that. Well, 96 is 4 less than 100. So 4 times 6
494.
less than 600.
494.
So what is that? 4 times 6 is
16. No, 24.
24. So I got to go 24 less than 600 is 576, right? So that gives you 7776, right?
No, I can never do that.
Yeah, you could. You really can. You really can. People can do, seriously, you can. People do amazing. People can spin plates on. You really can. If you just practice something, you can get better at it in a hurry. You sell yourself short. People do this all the time. Your capacity to do stuff is virtually unlimited. You just have to do it. I mean, if you use your brain and you use your body, it responds in ways where it improves, right? It really does. So you can do stuff like this if you just do it. You really can. Okay, what about this? This is a quick one.
Myself.
It's really quick. Good. Make some brain. Okay, the answer is you should be done. In fact, you could have been done in about 3 seconds or 2 seconds. What's the answer? N. How come?
Because it's negative.
Okay, because it's asking us to take an even root of a negative number, right? And what happens if you take an even root of a negative number? You're going to get back what? You're going to get i's in there somewhere, right? Now, where the i's, what the exact answer would be in terms of i's might be tough, but this isn't asking. What this is asking us for are real zeros, right? Or it wants us to provide a real number, and you can't do that, right? So the answer is N. Okay. What about this next one then? So this is N. What about this guy? We've got 256 to the 7/4. So this time it's written as a fractional exponent. So remind me, now we talked about this last week. Remind me how that works.
Don't you use the ternate so it makes a number?
So, okay, I can. I can turn it into a mixed number. If I want to, I don't need to this time though. I could, but I don't need to. That's an interesting way to think about it though.
Because don't you have to do, basically you get 2 parts but you times them. Wasn't it something like that?
Yeah, okay, so we'll come back to that because that's one way you can do it. Let's just think about this as,
Because if you reverse it, the 4 goes, so basically it was the square, it was not the square root, but it was the 4 to the root 256 to the 7th power, but then it's
Right,
down to
okay,
9.
so what we have to do is we have to decide, when we're taking the base 256 to the power of 7/4, we have to remember where each of these parts of the fraction goes in the radical expression. So if we write this as a radical, I want you guys to tell me what goes where. So what goes in the middle? Ariel, what number goes in the middle? 256. That's the base of the power, and so that's the base of the radicand, right? That's what goes inside the radical. So the 256 goes there. Sir, where does the 4 go?
Doesn't it go to the coefficient right there?
The index right there, right? Good. It goes right there. It's what sits on the radical. So it goes in front up on the little shelf on the radical. That tells us what kind of root it is, right? Okay, Audis, where does the 7 go? The 4 goes there. Where does the 7 go? Okay, so the 7 is just a regular exponent, right? So this is saying, well, there's two ways you can do this. We could either put the 7 there, right? Because what it really is the 4th root of 256 to the 7th. Everybody agree? Okay, or we could write it like this. Either way, right? Okay, which way is better? Because one of those is definitely much better, and this is kind of an important point. The second one is way better, way better. How come? How come, Caitlin? You're right.
Because, okay.
I just thought it was.
No, you're right. 256 to the 7th. What can you tell me about what that number is going to look like?
It's gonna be
It's going to be huge, right? So you're going to get this enormous number, and then you're going to have to take a 4th root of this enormous number. That's hard to do, okay? But if we take the 4th root first, that's helpful. What is the 4th root of 256?
Isn't it
18.
18. 27.
14? Okay, I'll just give you a hint. The 15 to the 4th is going to be about on the order of, I don't know, 400,000, 500,000 something.
Oh yeah, because 15 to the cubed is 250.
What is it? 8. Okay, 8 to the 4th would be about, it's huge, like 3,800 something.
2.
To the second.
2 to the 4th is 16.
4.
13. 4 to the 4 is 64. Or like 4 to the 3 is 64. 4 to the 4 is not. Is it 4 to the 4?
Oh, yeah, that's right.
It's 4, and here's how you can tell. Because 4 to the 4th is the same as 4 squared to the 2nd, right? 4 squared squared. What's 4
16
squared?
times 16.
Oh, 36.
No, 4 squared is
No.
8.
16.
I said 16.
16 squared is 256,
So why
right?
did you look at me like I was stupid?
I didn't. But there were so many, I probably didn't catch it. People were saying different things.
And then I said 8.
Okay, so this gives us 4 to the 7th, right? We can use our same trick as before, though. 4 to the 7th is the same thing as 4 to the 4th times 4 times 4 times 4, right? So what's 4 to the 4th?
256.
Good.
So much more time.
What's 256 times 4? That's a quick one.
A lot.
What's 250 times 4?
A lot.
1,000.
1,000,
Yeah.
right? So 1,024, very good. Because then you got another 6 times 4 there, okay? So that's 1,024 times 4. What's 1,024 times 4?
4,000.
That's it. Because 4 times 24, that's good. If you multiply by 4, you just double it twice. 24 and 24 is 48. Doubled again is 96. Okay? Now this one gets a little trickier, but we can do it. 4 times 4,000 is what? right? Plus 4 times 96, that's easy. That's just 4 times 100 minus 4 times 4, right? So say it again. So it's going to be 4 times 100. 96 plus 4 would be 100, right? So that's an even number, right? So 400 minus 16. 384. How come? 4 times 100 is 400, and I got to subtract away 4 times that 4.
16,384.
Right? So 16,384.
I said 82. Oh, darn.
I didn't see that one coming.
Okay, last one. Last one. Simple one. What about this? So I want you to rewrite.
How does?
Don't
Say it
rewrite
again.
it. That's like the simplest one. That's like the simplest one ever.
It is. I want you to rewrite this using a rational exponent. Very simple. So what's the base?
11.
Oops. Okay, so I've got a fractional exponent. What goes in the numerator?
12.
Okay, what goes in the denominator?
7.
Why?
That's it.
That's it?
That's it.
Every
That's it. Okay.
Hey, I did it.
How do you know why?
Okay.
Why can't you do that mixed number thing with that one?
Well, you could. You could, but it's not really going to help us. Now let's go back to this other one for just a second because Kenzie had an interesting idea. I want to make sure we see this here. So if we write 256 to the 7/4, right? 7/4 as a mixed number is 1 3/4, right? So we could write that as 256 to the 1 plus
That'd be awkward.
3/4. No, it's okay. This works out fine. Because look what you get. It actually saves a little time. What you really get then, that's the same thing. Where can we? I need a little more space. Here, let me. (256) to the 1 plus 3/4. Now think about your properties of exponents. If I have something like a to the m plus n, isn't that the same thing as a to the m times a to the n?
Yep.
Right? Because when I multiply like bases, I add the exponents, right? Everybody agree? So this is the same thing as 256 to the 1 times 256 to the 3/4, right? Everybody agree? Okay, well, we said the 4th root of 256 is 4, right? So I could rewrite this as 256 times the 4th root of 256 cubed. That's all that is, correct? Which is just 4 cubed. So this really just works out to be 256 times 64. Exactly. Right? So it works, doesn't it? And that's really, on this previous page, where'd it go?
You hit the wrong button.
There we go. So on this previous page here, isn't that really all we did right there? We took 256 times 64, just times 4 times 4 times 4. So look how quickly that got us to that spot right there. So it was good thinking. I mean, you can't do that. You just don't have to, right?
Is it easier?
6 and 1, half dozen the other. But it helps in math to be able to see how they're consistent. The more you can see how they're just two ways of saying the same thing, the better you get at math. Okay, let's see. So Casey, how about this one? I want you to rewrite this one using a radical, please. So 41 to the 2/7.
The radicand.
So the 7 goes where? Okay, so right there, good. And then 2, right? Or if I want to, I can put the 2 up there, right? Either way. Either way, right? Okay, good. All right, next issue. Okay, so now this is review, but we're getting into some stuff that's going to be a little less review, right? So this is stuff that we did
16.
in Module 3, right? If we're trying to simplify, sure, we get that, right? Write us in simplest form. But we also want to write this with minimal radicands. Okay, what's it mean to write it with a minimal radicand? What's the radicand there?
Stuff inside the
32. Yeah, the stuff inside the radical. So writing with minimal radicands, remember, that's what we would have said earlier in the year in Module 3. We talked about that as getting as much as we can out of the radical. So what's left in the radical is as small as possible, right? So how do we do that? What's our strategy for simplifying a square root like this? Okay, well, is 32 a perfect square?
No.
It's not. So then we're going to start moving up the list of perfect squares from half of the radicand. Half of 32 is 16, and that happens to just work, doesn't it? Right? So we could break this apart into, I've got a 16 times 2 is 32, so I get the square root of 16 times the square root of 2. I'm going to circle the square root of 16 because what does it do?
It's perfect square.
It becomes an integer, right? It becomes, or a whole number. It becomes a 4. 4 square root of 2. So that's written with minimal radicands because 2 is the smallest number we can, that's the best we can do in the radical, right? We can't get any lower than that because there's no perfect square factor of 2. But we got as much as possible out of the radical, right? Okay, so what about this one? All right, so what about this one? It's a little different. Now I've got the cube root of 375. So this time our thinking is just like it was in Module 3, but extended, right? Because now that's not a square root, it's a cube root. So instead of looking for perfect square factors of the radicand, I'm looking for what? Perfect cube factors of the radicand. Okay, so let's make a quick little list here of perfect cubes. So what's 2 cubed? 3 cubed?
27.
4 cubed? 5 cubed?
215. Oh wait, no, sorry.
6 cubed?
216.
7 cubed?
Not sure.
375.
No. 343. And then from there on it just gets, they get pretty big. So 8 cubed
I tried.
is what? You remember?
8 times 8 times 8.
Yeah. 512. What about 9 cubed?
Yes. 1,000.
No.
800.
No.
I don't know.
4,000 times 81.
729. Just 81 times 9, right? Okay,
Oh, yeah.
right? Because 80 times 9 is 720. 1 times 9 is 9, right? No big deal.
1,000.
10 cubed is 1,000. Good. Okay, so looking at our list then, 375 is not on the list, right?
Nope.
Half of 375 would be high 100s, agreed? You don't have to be even exact. So high 100s, it's going to fall right in there, right? We just got to look up from there. Agreed?
Yes.
Okay, so we'll just try them. Either we'll cross them off or we'll use it. Does 125 divide into 375?
Yeah.
It does. How many times?
3.
3. Okay, so we could write this as the cube root of 125 times the cube root of what? 125 times what is 375? 3. Okay, I'll circle that because the cube root of 125 is 5. So there's our answer, right?
So you leave the little 3 out.
You would. You have to leave that there because it's a cube root. It's not a square root, right? Okay? All right. Next issue. Something like this. Okay, how do we did stuff like this in Module 3 also. Okay, we added one set of directions here to this problem. So you got to read these directions. Simplify, sure. Write with minimal radicands, got it. But there's another set of instructions there. Rationalize the denominator. What's it mean to rationalize the denominator? Yeah, good. Okay, you can't have any stranded radicals in the bottom, right? So we're rational, meaning we have to turn the bottom into a rational number. We can't have the square root. Okay, so yeah, we could. We could just, like when we had a simple one, like let's say we had something like 2 divided by the square root of 3. What do we do to get the radical off the bottom?
Radical 3.
Okay, what'd that give us on the bottom?
3.
3. Now let's think about why it gave us 3 for a second.
Because 1.
It gave us 3 because if I multiply the square root of 3 times the square root of 3, that's giving me the square root of 3 squared on the bottom, right? Think about this now. a square root of something squared, those cancel, right? Everybody agree? If I think about that in terms of rational exponents, what would that look like? Well, there's a little 2 there on the square root, isn't there?
It'd be 2 over 2, which is
Exactly, it'd be 2 over 2. It'd be 3 to the 2 over 2, which is 3 to the 1, which is what I want. It gives me 3 on the bottom, right?
1. And then you get 2 times radical 3.
2 radical 3 on the top. So my answer would have been 2 radical 3 over 3. Okay, good. So it seems then like what I could do over here is the same thing, right? Okay, so what's the suggestion here then? Multiply top and bottom by the square root of 192. It would work, but there's got to be a better way, hopefully, right? Yeah, let's try to simplify it first. Because if I do that, I mean, look what that's going to give me. On the top, that's going to give me the square root of 1,920, and on the bottom, I get 192. That's a pretty big, ugly problem. I've got to simplify that big radical on the top then, right? That doesn't seem like a lot of fun. That's a lot of work, right? We can do better with this, though. So what if, like Justin suggests, we try to simplify this first? Well, the square root of 10 is already simplified, but we should be able to simplify the bottom, right? We should be able to minimize that radicand. Find a perfect square factor of 192. 192 is not a perfect square, right? But what half of 192 is just a little less than 100?
Yeah.
So we'll look right here, right? So we're just going to work our way up from there. Is 81 a factor of 192? It's not. It's not. 2 times 81 is 162, so it's going to miss it, isn't it? It's going to step over 192. Agreed? What about 64? It is. 64 times what? Okay, times 3. Okay, so Kenzie,
Yes.
then if we're going to break this up, so we found a perfect square factor of 192. So we're going to write the bottom as the square root of 64 times square root of 3, and we'll circle that one with a radical 10 on the top. Okay, right? We good? So what does that become?
It'd be 4 times radical 3 on the bottom with radical 10 on top.
Okay, so I'm going to get on the top, I'm going to get my
Radical 10.
radical 10. What is the
4.
square root of 6? No, square root of 64.
Oh, square root of 64 is 8. Sorry.
Okay, so now look at that. That's much easier. Now what's my stranded radical?
3.
Square root of 3. That's easy. So now I multiply top and bottom by square root of 3. Okay, good.
And then
Right,
don't
so
you get
then,
8 times 3, which is, I don't know, 24?
so that becomes 3.
Yeah, so you
Right.
get 24 on the bottom and radical 3, or 10 times radical 3 on top.
Okay, so what's the square root? No, let's not get hasty here. What's the square root of 10 times the square root of 3? Alexis, what do you think? What's the square root of 10 times the square root of 3? Well, think what we did up here. We said the square root of 192 was the square root of 64 times the square root of 3. Because 64 times 3 is 192. So a lot of times we'll take a big number under the radical and split it apart into factors, but it works both ways, right? Wouldn't you agree that the square root of 64 times the square root of 3 is the square root of 64 times 3, 192? So what's the square root of 10 times the square root of 3? Square root of 30. Yeah. No, you were right. Okay, does that make sense? Okay, so last one. We got to get through this one. So we got 8 minutes. So I want listen, I want everybody to dig deep here and just focus. This is a lot of stuff, but tomorrow you're going to get a work day. Okay, so everybody face front. Kids, face front. Laser eyes right up here. Okay, so what about this? This is the one I want to get through because this is the one that's a little bit different. And we got to really think about this. You got to turn on really, let's grow those dendrites. So cube root of 3 over the cube root of 40. Well, I'm going to probably try to simplify as much as I can before I try to rationalize the denominator, right? 3 we're done with, but is there a perfect cube factor of 40? There is. 8. 2 cubed is 8, right? So we could rewrite this as the cube root of 3 divided by the cube root of 8 times the cube root of 5. And what's the cube root of 8?
Oh, that's what you do.
2. Okay, so that's good. Then we end up with the cube root of 3 over 2 times the cube root of 5. Okay, but here's where we got to be a little careful, where it's a little different. We can't just multiply the top and bottom by the cube root of 5 anymore, like we did before, right? Because if I do that, I'm going to get the cube root of 25, and 25 is not a perfect cube. Think about why we did what we did in the last problem. We had an example, like for example, if we had 2 over the cube root of, or the square root of 3, sorry. And I'm going to write the 2 there, even though we normally don't, on the square root. We multiplied top and bottom by, keep doing that, by the square root of 3. I keep doing that, can't stop. So then on the bottom, we ended up with the square root of 3 squared, right? Make sense? Okay, we got to do the same thing here. I've got the cube root of 5 to the 1. What am I going to multiply the top and bottom by? The cube root of 5, no, squared, right? I'm going to multiply top and bottom by the cube root of 5 squared, because look what we've got then. In here I've got the cube root of 5 to the 1 times the cube root of 5 squared. Well, that's the cube root of what? What's 5 to the 1 times 5 to the 2? 5 to the 3, right? And so we'd get then, on the bottom of our fraction, we'd get 2 times the cube root of 5 cubed. Well, what does a cube root do to a cube? Cancels it, right? Okay, there's another way of thinking about this, though. This is where the rational exponents really make sense. Okay, if we go up to this spot, let's go up to this spot right here. Right, so if we're at the point where we've got the cube root of 3 over 2 times the cube root of 5. Let's write those with rational exponents. How could I write the top? The top is 3 to what power? The cube root of 3 is 3 to what power? No. Where does that 3 go? The denominator, right? And I've just got a 1 there, don't I? Right? So that's like 3 to the 1/3 divided by 2 times 5 to the 1/3. Right? Everybody agree? So when you see, now here's the connection I want you to make. When you see a fractional exponent like that, that means radical, doesn't it? Right? It's not a radical if the exponent is an integer. That's different, right? Or a whole number. If I get 5 squared or 5 cubed, those are whole numbers, right? But if I get 5 to a fractional power, that's a radical. So I've got it by getting the radical off the bottom. That's the very same thing as getting the exponent to be a non-fraction, getting it to be a whole number, right? So think about it this way then. If I want to get rid of this radical on the bottom, I've got to multiply by 5 to what power? Now, when I multiply by like bases, so on the bottom I'm going to get 5 to what power? When I multiply by like bases, I add the exponents. So you're really just asking yourself the question, 1/3 plus what would be convenient? 2/3. You see that? Because 1/3 plus 2/3 is 1. And what's 5 to the 1? 5, right? See what I'm saying? Right? So we'll multiply top and bottom by 5 to the 2/3. Then on the bottom, look what this gives us. That's 5 to the 3/3, which is 5 to the 1. Right? So we end up getting on the bottom 2 times 5 to the 1. What about the top? Well, this is the same thing. If I turn these back into radicals, 3 to the 1/3 is what is a radical? Cube root of 3. What's 5 to the 2/3? Where does the 3 go? Okay, connect, it's the index, right? So it's going to be a cube root of 5 to what power?
Second.
I'm gonna put the number, the 2 inside this time. What is 5 squared? 25, right? And 25 times 3 is just 75. See how that works? So then we end up with, on the bottom, 2 times 5 is 10. On the top, we get a cube root of 3 times a cube root of 25, which is equal to the cube root of 75 over 10. See how it works?
What was the beginning?
So the beginning of the problem was clear up here, right? All we did was, but we simplified that and we got a 2 times the cube root of 5, which is 5 to the 1/3.
Okay.
So we multiply by 5 to the 2/3 to get 5 to the 1,
Okay.
right? Got it?
I was lost.
Okay.